Hey guys, so today we're looking at Algebra 3's 2.5, where we are wrapping up Chapter 2, and we've only got a couple sections left after this one. And this section really is super important. It's one of the most fundamentally important concepts in algebra, if you ask me, which makes it one of the most important in mathematics as far as you're concerned. So this idea, like today's lesson is about transformations of functions, and particularly being able to identify them without having to do any work, right? So this is going to come with a lot of, well, to be totally fair, it's you'll have to memorize some things, and I know a lot of the time people like to whine whenever they're told to memorize something in math, um, but I mean, you memorize things in like literally every other subject you do. Learning is about memorizing, to an extent. So, I mean, I'll do my best to lay the foundation to make the memorization easier, but that's what's going to happen. And the reason why I think this is so important is because so much of what you do in math later on, like when I'm teaching calculus, so much of what we do relies on understanding the type of function you're dealing with, its possibilities, and being able to figure those out without using a calculator just by looking at the function gives you so much of an advantage over someone who can't do that. And like I can look at a function and immediately be able to tell its domain and range, what it looks like, what types of values you can expect to get out of it, that kind of thing. And all of that comes from this lesson. It stems from this lesson. So try to take this seriously. I think it's very important. And I know I say that a lot. Hang on. I know I say that a lot. Um, but this is more important than those other times, right? So we'll be looking at functions, parent functions, and transformations of functions, and how to find transformations of functions just by looking at them. So let's start by looking at what a parent function is. A parent function, and this is my own like definition of it, is the most basic form of a function type. And by function type, I mean like a line is one type of function, a quadratic is another type of function, right? A cubic function is another type of function, and so on. And then you've got absolute value functions and inverse functions and reciprocal functions, which are close to the same thing in certain cases, rational functions, and so on. So we'll start with the basics and work our way through several today. F of x equals x. Right, this is your typical linear function, which makes a line. Okay, and if you're confused, if saying f of x equals x is a confusing thing to you, like try to get over that naming fear. This is just like saying y. Okay, it's more precise. It's a function, which is what the f part stands for, dealing in the variable x. Right. So all your variables inside your function will be x. Well, I'll leave it at that. That's not strictly speaking true, but that's fine. So here we've got f of x equals the absolute value of x, and the absolute value looks like a v. And let's get a little more precise here. So when you just have y equals x or f of x equals x, it, the main idea is that whatever you plug in is the same thing that you get out, right? So if y equals x, regardless of what you plug into x, that is exactly what you'll get out for y. So if you plug in 0 for x, you get 0 out for y. If you plug in 2 for x, you get 2 out for y. If you plug in 10 for x, you get 10 out for y. And the same is true with the negatives. If you plug in negative 10 for x, you will get negative 10 for y because x equals y. And it creates this diagonal line straight across the origin. Just like this. Now, the absolute value of x, right, over here. F of x equals the absolute value of x. This is a v because if you plug in any number into x, it will always, like the function, based on the absolute values like definition, it makes that value positive. So say you plug in 10. Well, 10 is already positive, so the y value would be 10. So you plug in 5 for x, you get out 5 for y. So if you look on this side of the graph, right, the absolute value function works exactly the same as a linear function. So, and the reason I say that is because if you plugged in 0, you'd get 0. If you plugged in, 2, you would get 2, because the absolute value of 2 is 2. If you plugged in 10, you would get 10, because the absolute value of 10 is 10. However, if you plug in negative numbers, something interesting happens. Well, maybe not interesting to you, but something significant happens. Something different. And that is that if you plug in any negative value, when you take its absolute value, it makes it positive. So if you plugged in negative 10 for x, you would get positive 10 out for y. And it creates this v. And this is why our v shape happens. So why I'm going over this is just to, lay the groundwork for you to figure out what's going on. And you will need to memorize I would prefer you memorize each of these function types. It defeats the purpose if you need to pull out a table of values to go over them. So you really should memorize them. So moving on. A squared function, a quadratic. When you have a polynomial where the highest exponent is 2, this is a quadratic function. And quadratics look like u's to a degree. So the parent function is the simplest type of quadratic. And that's something I failed to mention. All right, up here, talking about parent functions. The most basic form of a function type. If you were to try to give me an equation of a line, there is no way, regardless of the type of line you give me, there is no way it can have anything less than what I have here. That is what it means to be a parent function. That every other type of line is merely a transformation of this one. And the same is true with absolute values. All absolute value functions will have absolute value and a variable in it. It's required. So this is the most basic of all absolute value functions. Any other absolute value function like that is an absolute value function. But it is merely a transformation of this one here. And we'll talk about how it's transformed and how you can easily identify everything about the transformation. But anyway, this is the most basic type of parabola, a quadratic function. Just f of x equals x squared, just x squared. And what this is you just plug in a number for x, get a number out for y. It just squares your value. Now, an interesting thing about raising to an even power is that if you plug in a negative number raised to an even power will always be positive. And it revolves around understanding what an exponent is. X squared means x times itself twice. And any negative number times itself an even number of times will always give you positives. And the reason for this is because the negatives will always have a pair. So if it's squared, and you say you have a negative times a negative, well, these pair off and make a positive. If you have, to the fourth power, so a negative times a negative times a negative times a negative, well, these would pair and these would pair, making two positive numbers. And then those would multiply, making a positive number, because positives times positives equal positives. And that idea continues, where since it's an even number, you can always find a pair for the negative, which would cancel it out. Well, essentially cancel it out. So this is going to give us only positive values for y in this format here. So if you plug in 1, you square it, you get 1. But if you plug in negative 1, that is also positive 1. Plug in 2, and you get 4. Plug in negative 2, and you also get 4, because negative 2 times negative 2 is positive 4. And it creates this parabola. A nice U shape. Okay. Moving on to the cubic function. Well, here is you have a strange curve going on. However, it is allowed to be negative. Because if you take a negative number and times it by itself 3 times, 2 of those times they'll pair off and create a positive number. Like say -2 times -2 times -2, right? 2 of them will pair off and become positive, but that result will always end up multiplying by another negative, creating a negative number. This is why a negative number raised to an odd power will always end up being negative. That's like a fundamental idea that I think everybody should know if you're in algebra, especially here in algebra 3. So start plugging in values. Plug in 0, you get 0. Plug in 2 and you get 8. Plug in 1 and you get, actually I want to do this in a different color. Plug in 1 and you get 1, and plug in 2 and you get 8. Plug in -1 and you get -1. Plug in -2 and you get -8. And what it creates is this interesting let's see if I can do it. Now, I want to be clear about this graph. There are no vertical asymptotes here, okay? It's not like you can say, oh, it's never going to pass this point and it's never going to pass this point. This is not a true statement. It is going to continually go left and right forever. Now, that's something else I want to point out. So far, every one of these graphs that I've graphed have a domain of all real numbers. That is to say that every value of x is allowed to be plugged into your function. There's no value of x that you can't just plug in here. There's no value of x that you cannot take the absolute value of. There's no value of x that you're not allowed to square. There's no value of x that you're not allowed to cube. So that means that all of these functions have all real numbers for their domain. However, this last one is special. This function, if you were to plug in numbers, plug in 0, square root of 0 is 0. Plug in 1, the square root of 1 is 1. Plug in 4, and the square root of 4 is 2. Plug in 3, and the square root of 3 is 9. Or, wait, what? No. Plug in 9, and the square root of 9 is 3. Sorry, I'm trying not to go on autopilot, but it's late at night, and, whatever. So, you get this curve that looks like this. And it would continue trailing up just kind of slowly, all right? So what I want to point out is what happens over here for the negatives. You cannot evaluate the square root of a negative value and get a real number answer, because square roots aren't defined for negatives. The square root of a number is thinking what times itself gives you this, right? But negatives, you can't multiply 2 numbers times themselves and give you a negative value. Or 2 real numbers anyway. So square roots will start somewhere and then trail off to some direction based on the transformation. And the domain here is not all real numbers. You are not allowed to plug whatever you would like under this radical. So the parent function would have a domain of only positive x's or 0. So x's that are greater than or equal to 0. Because negatives don't work under even roots. Now, let's look at some transformations here. And I'm going to start going through these pretty quickly. I wanted to get that out of the way pretty slowly. We're going to start ramping things up. So this is a vertical shift. This is what you do to functions if you want to move the entire thing up or down. Right? If you want to make vertical shifts, this is how you do it. You add or subtract something to the end of the function. And this end is not necessarily true. It's just how it's most typically seen. It's really just adding or subtracting something to the function itself. So if you had y equals x plus 1 and y equals 1 plus x, these give you exactly the same function. And it's a transformation of the parent function. It has the parent inside the y equals x part, but it's also got this plus 1 here. And what the plus 1 does is it takes whatever the x value you plugged in and adds 1 to it, and that's the y value. So it will take, if you plug in 0, here's the parent function. I'll graph the parent. Here's the parent function. And I'll change this 1 to to something more significant so that it's easier to see on the graph. I'll change it to a 4. So both of these will be exactly the same line. Right? So I'll just graph one of them, right? So basically, whatever you plug in for x, you're going to add 4 to that, and that will be your y value. So you'll add 4. So say we plug in 0. Now it's going to add 4 to that. So 0 plus 4, that will be your y value. So 1, 2, 3, 4. So 4 is your y value. So when we plugged in 0 on the parent function, we got 0. But when we plugged in 0 to this transformed function, we got 4. If you plug in 10, you'll get 14. So if we plugged in 10 earlier, we would have gotten just 10. So the idea is every value that we would have gotten is now gone up by 4. And so you get this right here. Right, this parallel line that's 4 above. However, the same is true, like the same idea holds if you're subtracting, like if you have f of x equals x minus 3, right? This looks like the blue line, except moved down 3. Every single point has moved down 3 when you compare. Absolute value functions do the same thing. So the parent function looks like this. And if you were to add or subtract something like y equals the absolute value of x minus 4, or let's do, I'm getting bored of 4, let's do 5. Then this is to say, I'll color it in red to show you I'm graphing it in red. It's exactly this function moved down 5, and I can realize that by looking at the function. So I didn't plug in a table of values. I'm not doing anything. I'm just using the knowledge that I've just now acquired if I'm new. And so that's to say that it's this function, but moved down 5. And it's moved down 5 because it's a minus sign. If it was plus, it'd move up 5. And so you go down 1, 2, 3, 4, 5, and then it's the same type of function. 1, 2, 3, 4, 5. I'm sure you guys get the idea. 1, 2, 3, 4, 5, and you get a v. And so we've got this vertical shift. The same would be true for this function. If you've got f of x equals x squared minus, actually let's do plus 3. Then instead of being a parabola centered at 0, 0, you're going to move up 3. And it will look like this. Something like that. All right. And the same is true for both of these other function types. So the cubed function looks like this by default. Something like that. And if you were to shift that up and down, this whole thing would just move up and down. So if you had y equals x to the third minus 2, y equals x to the third plus 1, y equals x to the third plus pi, y equals x to the third minus e, y equals x to the third plus 4.1. This means it would go down 2, up 1, up by pi, down by e, up by 4.1. All of these things do the same thing to the parent function. They just move your graph up or down by something. The same would be true here. I'm not going to go over this, but it's the same idea. Now, horizontal shifts. Horizontal shifts are, they look a little different in terms of how the function looks after it's been shifted. Well, I mean how the problem would look based on it being a horizontal shift, and I'll show you. So we're going to skip the line and move right on to the more complicated functions because lines horizontally shifting are very redundant, and I think it just serves to confuse students. So we won't even talk about it. So to horizontally shift a graph, you have to figure out, remember what's important about the graph, what makes it the function type that it is, and if you add or subtract something within that function type, that special thing, it will horizontally shift the graph. So what's special about this graph, it's an absolute value function, right? So that's what makes it special, the absolute value bars. So if you add or subtract something within the absolute value bars, then it's going to horizontally shift your graph. You can plug in tables of values and verify this, but it is true. So f of x equals the absolute value of x minus 3. Or f of x, we'll do this in a different color, f of x equals absolute value of x plus 3. All right? If you were to use a table of values, I would just recommend you trust me, or you can stop it and verify. But if you use a table of values to check this, a minus 3 inside here will move your graph, your absolute value parent function, to the right by 3 units. If you add 3 inside the thing that makes it special, the absolute value in this case, it moves it left by 3. So instead of your v being right here, instead of your v looking like this, if I can not suck at this, you're going to go right 3 for this one. So 1, 2, 3, and all the points move right 3. 1, 2, 3, 1, 2, 3. And then all these points move right 3. 1, 2, 3, and you get this v. And this one moves it left 3. So left 3, left 3, left 3. Just like that. All right? The same is true with all these other functions. If you were to take this one, and you've got f of x equals, actually I want to show you what these look like. The thing that makes this important is that we are taking something and squaring it, right? So what it means to be like within the special function type is we want to take more things and square it. Here we took more things, we took the absolute value of more stuff. Here we want to square more stuff. That's how you'll make a horizontal shift. So this would look like this. So look, now we're taking x minus 4 and squaring it. Here we're taking x plus 3 and squaring it. And this is going to give us a horizontal shift, just like taking x minus 3's absolute value gave us a horizontal shift. So you might be able to tell, but a minus will move it right, and a plus will move it left. And it's a parabola, so this is the parent function-ish, and it will move left and right based on these numbers here, okay? Cubed function, you get the same kind of thing as the squared function, where this would be a shift to the left by 2. Whoops, we're cubed now. This would be a shift to the right by e. This would be a shift to the left by 11.2. So pluses, like a plus inside here moves it left, a minus inside here will move it right, okay? And it looks like this for square root functions. That's moving right 3, right 4. I don't even know what number that is. That's moving it left 3 and left 4, okay? So, moving on. Reflecting about the x-axis. Now, to do this, all you need to do is put a negative sign in front of the function. So, this would be reflected over the x-axis. And what that is to say is that you take your v, in this case it's a v because it's an absolute value, and it will be reflected over this axis here. So this is the axis, and you're sort of flipping it over it. And you get this upside down looking graph. That's what an x-axis reflection would look like. In this case, you know, for any of you students who are watching this, who are really got it. In this case, a y-axis reflection is identical to the same graph as what we've got, and we have a term for that. And we'll go. Actually, we've already talked about the term. We just haven't defined it that way. this is an odd function. Odd functions are y-axis reflected, right? Pretty sure that's right. Yeah, it's got to be. It's got to be. So here we've got x squared, right? A negative x squared is going to look like this, upside down. A negative x cubed is going to look like this. Instead of curving up like this, it's going to curve like this, like that. And your square root function, instead of looking like this, it's going to flip over the axis and look like this. Well. Wow, that reminds me of an old YouTube video. If you've not heard of the YouTube video Star Wars According to a 3-Year-Old, you absolutely need to watch it. well, okay. All right. So lastly, one of the last things we're doing here is stretching and shrinking a graph. So if you multiply the function by a number, multiply the function, like what's important about the function, by some number, it will get stretched or shrank, shrink, narrowed or widened, however you want to think about it. All right. I'm not too important. Like, it's not too important for you to understand. Oh, this is a horizontal stretch, but a vertical shrink, and this is a vertical stretch, which is not a horizontal stretch. It's all BS, if you ask me. It's all the same. It basically just makes your graph either wider or more narrow, right? So what that looks like, and whenever you see it in a problem, is something like this. It's your function type with a number being multiplied by it. So what this is, since this number is a fraction, right? Since a is a fraction, it gets shrank or widened, right? So this would take your v and make it really like a third, like 3 times wider, basically. Instead of looking like that, it would be wider. Okay, that's the idea. And then if you had something like this. This is going to make it a lot more narrow. Instead of just looking like this, it's going to look like this. It's going to be like super steep. Man, this lesson is it's going on, so I'm trying to continue here. So this one inside the squared function, or the squared function, it's going to look like this. Like that's going to be a shrink, or it's going to make it wider. She's shrinking this current term. Doesn't even make sense. It does make mathematical sense. I just don't want to explain it to you because it would serve to confuse you, probably. So instead of looking like your typical kind of thin parabola, it's going to be wider. But if you've got like 6x squared, it's going to be a lot narrower. Still going to look like a U, but it's going to be super narrow, right? If the number in front is a fraction, it's going to be wider. If the number in front is a whole, like bigger than 1, not necessarily just a fraction, but bigger than 1, it's going to be more narrow, okay? So the same would be true here and here as well, okay? So multiple transformations. This is the important thing, and I'll try to get through this quickly. So a number in front, remember, we were just talking about this, is responsible for making our graph wider and more narrow. So it's bigger than 1, and so it's going to get more narrow. So this is narrow. You can call this narrower by factor of 2. And I've got a shorter version of this. It's VSBFO2. And this is a vertical stretch by a factor of 2. I'll know what that means. If it's a shrink, then I don't know. You should just call it widens, actually, because I don't like the term shrink, but whatever. So that's what this 2 does. Then the minus 3 inside here, we'll move it right 3. And what that will look like is, here's the parent function. Man, this is a long lesson. I apologize. It's 29 minutes and 40 seconds so far. But we're getting towards the end of it here. So that's what the parent function looks like. It's going to be narrower by a factor of 2 and moved right 3. So let's move it right 3. 1, 2, 3. So move this point right 3. Actually, we can't do that because it's going to be more narrow. So move the vertex, because that's not going to change, right? This is always the key. Move the vertex and then estimate the narrowness. I don't really care if it's super accurate. If I wanted super accurate graphs, I would tell you to get a graphing calculator out. What's most important is that you can identify the transformation without a calculator. So it's going to look like a more narrow V. And I think it looks like this. Instead of going up 1, out 1, it's up 2, out 1. So it looks like this. All right. Now, how about this one? This is 1/2 x squared minus 5. So you tell me, what do you think the 1/2 does? Look back if you have to. It widens the graph, makes it twice as wide. So this is widens by, just widens. All right, I'm just going to call it widens. And it's in this annoying to see color. So the technical term for this is like a vertical shrink by a factor of 2, but that's more complicated. The 1/2 will make the graph wider, right? That's what's really important here. And then what does this minus 5 do? Now, if you say it moves right 5, then you're forgetting that for it to move left and right, it has to be tied with what makes the function important. So it would have to be inside like a set of parentheses being squared. If it's just at the end, this is going to go down 5. So you've got to go, it's widened, and that's by the 1/2, and then the minus 5 makes it go down 5. So it's a parabola that looks like this by default. That's what the parent function looks like. Then our function is move down 5, 1, 2, 3, 4, 5, and it has become wider. I do not care about how much wider you make it. I mean, like I said earlier, if I wanted super accurate graphs, I would ask you to plot them using a calculator. I'm just wanting you to give me the transformations. Now, negative sign in the front, what does that do? That is an x-axis reflection. Reflect about x-axis. That's what this means. Reflect about x-axis. And then the plus 2 in here will move the graph left 2. And you can combine these. So here's the parent function. It's a cubed function, so it looks something like this. Our function is going to move left 2 and reflect over the x-axis. So left 2 and reflect over the x-axis. So it looks something like that. And finally, we're going to move this out here. All right, this is a y-axis reflection. Actually, I'll talk about it. It's at the very end of the lesson, but whatever. If you have a negative inside your function type, like if there was a negative in here or a negative in here, that is what's responsible for y-axis reflections. And so this is a y-axis reflection. All right, and this plus 1 moves the graph left 1, and the plus 4 moves the graph up 4. And something to point out with these y-axis reflections, I'm not going to put these on a test or anything probably, but I may as well talk about it. If you were to see this in a simplified form, it would look like this. It would look just like this, right? Because you distribute the negative. So then you would think, oh, there's a negative sign here, so it would be a y-axis reflection. But then you'd think it moves right 1, when in fact it moves left 1. Because for this statement to hold true about moving left and right, you need to factor out the negative sign first, which is what this has done, right? So this is already the correct form where it's factored out. So here you would have to factor it out before you can make a judgment about whether it's moved left or right. But anyway, so your standard function looks like this. Your y-axis reflection you want to do last. So you want to move it left 1 and up 4, left 1, up 4, and then it's got a y-axis reflection. All right, I'm pretty sure that's right. So yeah, we're good. All right, so there's your lesson. If I can find my mouse pointer. I've got so many like TVs and monitors hooked up to my computer now that I don't even know. So here's your homework. If I can figure out what is going on here. There we go. I repositioned the display settings. This has been a really long lesson. This will probably be the longest lesson you have all semester. Well, it's going to be a really long lesson. So there's your homework. Please do your homework. If you have any questions about the instructions, because they might be different from the way I've been teaching it here, like if they ask something random, ask me if the instructions are what you should be doing, okay? I'll try to tell you, but I might forget. All right, that's it. See ya.